So thank you all for participating again to the NSERC Cohesa seminars. We're very excited today to have Professor Lesley Shannon of Simon Fraser University doing a quick introduction of her work and herself. Lesley is one of our two pillars in the FPGA thrust, and we're looking forward to hear what she's working on and what her plans are for the NSERC Cohesa. She may also give a quick overview of her other work because it's very busy as always. Thank you, Lesley, for doing this.
Thank you for the invitation, and thank you everyone for taking time out of your day to listen. So I'm doing this in the perspective of presenting the work going on in my lab called the Reconfigurable Computing Lab. My interests really are heterogeneous computing system design using reconfigurable technology. So the aspects of that research I'm going to focus on today are hardware acceleration into multi-core computing systems and the project we have undergoing in that area. And that ties into what we're trying to do with Cohesa. So some of our initial work right now is to look at a platform for looking at the architectural work and being able to investigate how it actually builds in a physical system. Other work we're interested in is in programming distributed reconfigurable systems and making that accessible to a broader scope of people. Another side topic that I work on, well, it's a side topic in perspective of this talk, but a big chunk of my work has been in reconfigurable continuous flow microfluidics. So I'll just give you 2 slides of information on what that is, just because it's an interest of mine. And the newest topic that we've started working on is reliability and fault tolerance in non-critical reconfigurable systems. So that's particularly relevant for systems that have large numbers of FPGAs running applications for a while. So you can think of like data centers. So starting with our first one, looking at integrating hardware accelerators into multi-core systems. To be able to really look at this on an FPGA-based platform so we can understand memory interactions and things of that nature, we actually had to build a new soft processor because all other soft processors today feature fixed pipeline designs, which obviously limits the integration options and performance gains. So our new processor supports variable execution lengths for executional units as well as parallel execution of functional units.
Professor Shannon, maybe is it dropped?
Probably. Sorry, if anybody can hear, we cannot hear video from, we cannot hear audio from Lesley. So let's see, we're going to try to get her back.
It seems that she's connected, but yeah, though it's not sharing. She disconnected. So maybe wait a little bit. It's the same link. You can use the same link.
No other option.
No, I'm saying she will use the same link to message. Yeah.
As long as she understood that she's dropped and she's not talking. Okay.
Yeah. Should I mail her? Okay. Don't you just reconnect using the same link?
Hello?
Hello.
And I'm back.
Okay.
All right, let's try this again. My apologies, I'm currently traveling, so hotel internet is possibly not the most reliable thing. Okay. So I'm going to skip ahead a little bit simply because I've used some of my time trying to stay on the internet. Basically, we needed to create a platform that would let us look at integrating accelerator types that were from a tight perspective as well as a loose perspective, and would let us deal with the complexities of what that looks like. So the soft processor we created is called Taiga, which is a reference to Canada's fundal regions. So Taiga is the region of Canada in which you live, as opposed to the tundra. Hope you like it. The processor is open source, optimized for FPGAs. The current one is single core, single issue. It supports out of order execution and commit as well as precise interrupts. It supports independent variable latency execution units. And currently for the RISC-V 32-bit instruction set, atomics, basic integer data types, and multiply and divide, it's written in system Verilog. It's uploaded and you're welcome to download it. It's vendor independent, so you can run it on Altera or Xilinx devices should you choose. And we've done optimizations for both platforms. Really what we're trying to get to is a framework that looks like this, where we can have asymmetric multi-core configurations so that the CPUs have the same base ISA, but maybe not all of the same configurations. We want to allow tightly integrated accelerators within CPUs should we desire, as well as hardware accelerators that are treated as first-class citizens. So not devices, but actually as compute elements with extremely limited instruction sets. The ability to manage their own memory access, as well as DMA, atomic instructions, so mutex protections, everything that you might consider fundamental to being able to share data between processing units. So we're really interested in terms of building this soft processor to make this framework work, but also be scalable and have a good performance per LUT, particularly over fixed pipeline designs. So basically, we have succeeded in doing this. We have our out-of-order commit processor. Our performance efficiency compared to other open source RISC-V processors actually has a better MIPS per LUT than the other ones out there, largely because we have a much higher IPC. And we also were able to demonstrate a case study of integrating hardware accelerators showing kind of a worst case of what happens as you increase things. The pipeline is pretty simple. There's a fetch, decode, all of the functional units operate in parallel. You have the ability to replicate units of use to you. So, for example, if you're doing a lot of division, because in this architecture our division is not fully pipelined, you might replicate the divider for the particular applications you were running on this. Because we allow out-of-order execution and commit, there has to be ways to track that, which I'll show in the next page. We've got scratchpad support, as well as support for caches. So you can have accelerators or other instructions have scratchpad access to data or go through the caching system. We also have a branch predictor and everything else you need to support an OS. All of these things are configurable, so you can have a very stripped down version that doesn't have a divider, TLB, MMU, scratchpad, or branch predictor if you want. How we do early commit is very much FPGA specific. The closest thing to it is probably scoreboarding. It's not exactly the same, but it allows us to do execution out of order. But we're able to support precise exceptions by the way we flush the pipeline. Other than that, you're able to scale all of this to reflect the number of functional units you have in the pipeline, so you can figure out based on latency, initiation interval, and the number of functional units, how many instructions at max you might have in flight. You could scale this to multi-issue, but we're not currently doing that, and we don't have any plans to do so. In terms of resource usage, pico-RV is probably the smallest one of the current RISC-V processors. We went with RISC-V simply because we wanted to build a new processor architecture, and RISC-V provided us with all of the other support we needed in terms of debuggers, compilers, etc. However, even though RISC-V is has a much higher operating frequency and is slightly smaller, it's a multi-stage processor, so it's quite slow. Orca is relatively comparable in size and operating frequency. These are the Orca numbers. Orca's Guy and Lemieux's processor from UBC. These numbers are for the Xilinx devices. Their numbers look much better on Intel devices. Conversely, our numbers aren't quite as good on Intel devices, but are much better on Xilinx devices. We're giving you the numbers for fixed pipeline with no branch prediction, which is the baseline architecture. Relative to these, we looked at 2 different Orca-style processors, 4-stage versus 5-stage. After that, we looked at what cost to add a branch predictor and then what it cost to do an early commit. And as you can see from the baseline, it reduced our operating frequency by about 4%, and it added less than 10% to our number of slices, flip-flops, and LUTs. In our design, we use the BRAMs for the branch predictor, and we do our register file and lookup table memory, whereas the Orca device uses a register file in BRAM, which does cause a bit of a performance hit. So what are we looking at here? We're looking at some performance numbers, instructions per cycle for some basic benchmarks, and the key thing really to note here is that all of these top 4 bars are actually the Taiga processor operating, or IPCs. The lowest one is for that baseline, which was the fixed pipeline no branch predictor. The reason there's such a huge difference is that the way the previous generation of Orca was constructed and the current pico-RV architecture is constructed is that you couldn't actually do direct memory access. So you can have a tightly coupled, you could, in the old design of Orca, have a tightly coupled scratch pad memory, but when you had the device hooked up to a bus to talk to off-chip peripherals such as a UART, then that didn't work because you could only have one type of bus. Now, as of March, I want to say 13th, Orca has done a new release which includes a branch predictor as well as the ability to have multiple bus initiations. So we expect the new Orca design to fit somewhere between this red bar, the 3rd bar in, and the blue bar, which is the 4th bar in, because all of the red bars are our baseline. The blue one represents what happens when you just add a branch predictor. The green one represents what happens when you force in order, but you don't enforce a fixed pipeline. So that means we allow parallel execution. And the final bar shows what happens when not only you allow parallel execution, but allow early commit where it's appropriate. And in most cases, you'll see it makes quite a bit of a difference. The only benchmark for which it really makes no difference whatsoever is the RAND benchmark, because to generate all these random numbers, a ton of division operations are run. And if you may recall, the latency for that unit was 34 cycles along with an initiation interval of 34 cycles. So that delay dominates the numbers and there's really no benefit overall. Now, one of the great things about our design is that if we wanted to, we can actually replicate the divider, which all of a sudden would change these numbers quite drastically. I guess other than that, I wanted to say that overall, if we look at these numbers from a MIPS per LET perspective, we see an average of about a 28% improvement of having the out of order plus parallel execution units. So this for us is looking like a very promising platform for looking at tightly integrated accelerators. And for us, that ties into the machine learning work that everybody's doing, looking at potential tightly integrated instructions into the CPU architecture versus more loosely integrated, more complex accelerators. And accelerator integration matters. So if you think of the commercially available soft processors that allow accelerator integration, there's really two models. There's the NEOS model, where you integrate the accelerator into the execute pipeline, but since it's a fixed pipeline design, if it's a multi-cycle instruction, you stall the pipeline until you're actually able to get it through the execute phase. Conversely, Xilinx microblaze architecture actually allows you to write out and read back in the write back phase to a more coarse grain accelerator. So both of these have overheads compared to the design that we were interested in looking at, where we just add in a new custom instruction that then flows into the write back phase. So the accelerator we looked at was a very simple one. It's a bit ops unit with counting leading zeros and byte swap support. The reason we picked it was we wanted to look at something where we weren't going to register anything. So if the accelerator gets too complex, you're going to pipeline it and register it and allow it to actually flow quite a bit better. So we were looking for something that would be completely unregistered because we wanted to see what it would do to our operating frequency. And then we kept adding them. So we looked at our parallel execution units. We added first one of them, and then two, and then three, and then four. And it really wasn't until we added the fourth one, and if you keep going, you start to actually see any impact in terms of the frequency, the operating frequency of the overall processor. So really where we are here is we've got a good baseline for looking at integrating accelerator support. In the case of the Cohesa project, this is going to be for machine learning applications. One of the things we found, which was interesting, is that how you implement a FIFO on these different designs actually matters quite a bit, and you do have to implement them so you can decouple the different stages of the processor. And we can actually quite readily support additional execution units with really out impacting the frequency. And if we're looking at more complex ones, we believe that we'll even have a better or lesser impact as long as they're registered. So this leads us to Diffuse, which is our distributed front-end user framework for OS abstraction of hardware accelerators. So really it's a newer piece of work. We're right at the data collection phase, and we're looking at this as a runtime system for programmably distributed reconfigurable systems. So the original work was a front-end user framework for OS abstraction of hardware accelerators, an API that we built on top of Linux to abstract hardware accelerators functionality as analogous to threads. And in our example, we did POSIX threads. This paper was published before software as a service, but basically this is the same idea. So it provides transparency to software designers at the application level and OS support for easy hardware acceleration, with the idea that we wanted to extend software multitasking and programming models for mixed software hardware platforms so that the tasks are allowed to become executed as a software on a processor or as a custom accelerator without programmer involvement. And we wanted to make sure that doing all this didn't stall the processor, because before this work, what was happening is you spin off a task to be run on a hardware accelerator and the CPU would spin waiting for that task to come back. So basically we divided Fuse into a set of top-level policies and then a lower-level set of mechanisms where we basically, at runtime, allowed users to add in new hardware accelerators that could then be detected by the API running with the scheduler to determine whether any given thread would execute as a software thread or on a hardware accelerator. So it was quite limited because it wasn't in a multi-core system. And we did do some initial work to expand it to see if we could expand it to multi-core, and it looked quite promising. But we decided to go a different way, so we didn't really pursue that too much. It didn't, in the data that we actually did, we didn't actually bother even with DMA, and we still saw huge performance advantages. But again, there's no inherent reason why not to support DMA. We did, the solution at the time, because this was before the Linux device tree, was that we had to implement a kernel module driver for each new accelerator. And we recognized it as having multiple potential states, either being unloaded, loaded and in use, or loaded and not in use. And while this design seemed perfect for a runtime reconfigurable system, we actually didn't test it in that framing. So where we really wanted to go now was to look at these issues with a new distributed framework based on the same concept. So basically we want to be able to manage a distributed reconfigurable compute framework with software tasks and hardware tasks executing in unknown places. To address the limitations of the original work, we wanted to ease FPGA accelerator development and provide a generic accelerator driver from the software DMA and reconfiguration abilities. And then we wanted to extend Fuse to these distributed systems, which had a few options. We also moved from POSIX threads to OpenCL as the underlying model for computation, because this was going to be a more accessible way for software designers to actually create accelerators. So we allow a set of applications to be distributed across the nodes of a cluster. In our case, we don't assume security issues. So basically we assume that all the applications are coming from the same trusted location. The reason for this is that we're treating the accelerators as compute units. You can't interrupt the execution of a task on an accelerator, but if a compute accelerator is not currently in use, then some other task from some application that needs the same accelerator is capable of using it. So our tasks or OpenCL kernels from each application are scheduled to either the CPU or the FPGA-based accelerators based on the available resources. And what we're looking at is what factors should inform scheduling and contribute to application turnaround time. So obviously the big one is communication between nodes, between devices, because we don't want to move data more than necessary, or CPU binaries and FPGA configuration files, and the potential speed up of kernel execution on an accelerator in case there's more than one version available, and then what hardware accelerators are actually available and how are they currently configured. So some of this ties back to the original work. I just put this in here in case we actually posted these slides and somebody wanted more details, but basically we have a script-based flow to automate the construction of the accelerators and the configurations that leverages Xilinx tools, SDXL, and Vivado, and a generic accelerator driver. And then the runtime system is available, and we build all this on top of POCL, which is an OpenCL standard, an open source implementation of an OpenCL standard. And we are building this on top of a cluster of Xilinx development boards through a router switch. So the final thing I'm just going to briefly hint at, which I mentioned is another big area of work for me, which does not tie into any of the other projects, is micro-ROMs, which is a microfluidic reconfigurable on-site analyzer for multiplex samples. Basically, we wanted a portable sample analysis unit for microfluidic samples that was able to be reconfigured at runtime based on the actual samples being analyzed. So this architectural aspect, the reconfigurable microfluidic interconnect, as well as the runtime programming, simulation, and even some of the basic issues with scaling of initial designs is where I've worked on this. So this is a conceptual draw of how we did this with an example of a particular environmental biomolecular test called qPCR. And basically, when you look at it from a conceptual perspective, the fabric looks like kind of an FPGA. So some of the rules are the same, some are different. Obviously, it's much more three-dimensional because you can't allow liquids to mix unintentionally. So in closing, I'll say that we're hoping that Taiga will provide us a good baseline for adding in custom compute units for the Cohesa project. So right now we're working on Linux support and multi-core support. We expect to have that at the end of this summer. We're also looking at a next stage at a polymorphic vector architecture. So basically runtime reconfigurable vector support. And there's obviously the broader concept, but even a more specific concept maybe tied into machine learning. So you can look at it as a vector overlay specifically for machine learning that would be polymorphic. Right now our diffuse data collection is underway, and we're building a prototype of our multiplexing system as for microroams, as we've now got digitally controllable valves and a lot of the other main components you need, like sample wells, sensors, mixers, heaters, and everything else. And I'm going to leave off there in case anybody has any questions.
Thank you, Professor Shannon. So do we have any questions from participants? Please don't forget to unmute before you ask. Done? Could you, okay, so I have one. I could just, I find it rather interesting as part of the future work when you talked about polymorphic vector architectures. So would you be able to elaborate a little bit on this in terms of what do you see as the immediate benefit in terms of machine learning applications?
So there's two parts to this. So RISC-V has support for a polymorphic vector ISA. Not all of that's related to machine learning, but the part that could be interesting is from the machine learning perspective is you can at runtime configure data widths. You can also at runtime configure how many instructions execute in parallel. So I guess the interesting part is taking the polymorphic vector architecture that's part of the proposed new additions to the RISC-V ISA and overlaying, I'm going to say, custom instructions into that are more suited to machine learning. So more neural network-based components.
Okay, that makes sense.
That helped?
Yeah. Anyone else?
To be able to do this, I was going to say one thing we are doing to be able to do this is Steve and I are working together. I'm assuming he's probably talked about this to look at some benchmarks for FPGA fabric. And I believe that some of that will actually flow into this work as well.
Yeah, I think Professor Wilson touched upon the subject last time. That's true, during the other presentation.
So that's why I didn't touch upon it.
Yeah, okay.
There's no reason to repeat that.
It makes sense, makes sense. Do we have any other questions? Well, if not, I mean, the presentation and the video will be available anyways after 1 or 2 business days. And you know, if anyone has any questions, specific questions, sorry, then you know they can. I'm assuming they can email you or contact you.
Absolutely. Thank everyone for your time, and my apologies for the technical difficulties.
Thank you so much, Professor Shannon, and thanks everyone for participating. I think the next, I believe the next seminar is taking place on May 28th, if I'm not mistaken. It's Professor Mazoom Hossein who is going to be talking, but we'll make an announcement in the next week or so and keep you posted. And thanks again, everyone, for thanks again for joining today. Have a good day.
Thank you for organizing.
Thank you.